Hello viewers and welcome to another episode of Space Science with Python. Now the last time we were talking about how to set up a Python developing environment using remote containers and Docker, and I hope you liked it and you'll see also the advantages of using this kind of environmental setup. We will use it also today and also in the next couple of videos and tutorials. So I will give you just a quick recap of last time to help you set it up again, because I created now a Github repository for you where everything will be stored. So last time VS Code, the third video of the tutorial series, is created here in the folder. And now in the general main folder, we have now the Docker file, a requirements.txt, and also a dev container with the JSON file that contains some settings for VS Code itself. And we will use it today and also in the future tutorials. And each tutorial video will contain the code in individual folders. So you will see how this tutorial repository will grow over time. Now, today we will talk a little about actual space science, so not a third video about setting up an environment or something. And we will use the Earth as a first example to get in touch with space science functions, or a library that is commonly used in space science. Now, you know, in data science and so on, we have a lot of libraries, machine learning, and a lot of tutorials for this, but space science is not well covered. And what kind of libraries are there? And today I will show you a library that is also, it has been developed. It's now being developed since, I don't know, years, even decades by NASA. It's not known in the, let's say, amateur coder community. It's really used by the scientists. It's huge, so it will, we will work with it really in the next dozens of tutorial videos. We will use it because it's extremely mighty and it's very complex. So please don't feel intimidated maybe by how this library is set up, where the files are all stored online, and how to configure everything. I use this this library now since 9 years, and everything was learning by doing, and there was a lot of pain, a lot of tears. So please, I just now give you the simple approach to learn this library, and let's start with it. We will talk as again. We will work on some Earth-related topic. So we will compute the position of the Earth in our solar system and see whether the results make sense. And for this, we will create a new folder today, simply called For the Earth, same as the YouTube video title. Now let's go to our VS Code environment, and we have here now the YouTube tutorial main folder. The Earth has been created, and now we can rebuild and reopen the container. So a small recap from last time. You press Shift Command P. You need to have Docker installed and running, VS Code, and the extension remote containers. And now we rebuild and reopen the container, or when it's the first time for you, open folder and container, and the container is being built. Now let's click on it. We see now in the log that the file, the Docker container, the environment is being created. This may take some minutes or some seconds, and we'll wait for the setup. Now set up, it only took us like half a minute to set everything up, and now we can start computing our Earth parameters and so on. But how do we do this? Well, I installed a package called Spice that we will use now and also in the future tutorial. And let's move to maybe the documentation of Spice. So all the links are provided in the description. So here you can see the website. It appears a little bit old-fashioned, I would say. It's from JPL, and current version is now version 66 from 2017. You think, well, it looks a little bit old-fashioned, and the toolkit is provided in C, Fortran, even IDL, MATLAB. So you are maybe a little bit suspicious. Well, is this really a modern tool? And I can tell you that SPICE is being used in space science and engineering for decades now. And it provides everything. You can compute the position of planets, the appearance in the sky, you can compute distances, the velocity, even the trajectory of spacecraft, the orientation of the instruments, the rotation, and all these parameters. So it helps space scientists to understand spacecraft missions, the planets, and also to interpret the data. And this is really an extremely mighty tool. You may remember also the landing of Perseverance a few months ago, and we will use SPICE also in one of the future tutorials to compute the landing trajectory of Perseverance on Mars and even use the Mars coordinates and everything. So be prepared to really do some awesome stuff. Now, SPICE, the website has also a very sophisticated documentation and also a lot of tutorials. So there are tutorials, I think around 50 or so, yeah, and they're quite huge. I will not cover everything now. We will just, we will do learning by doing. I will also, let's say, provoke some errors to show you how SPICE behaves and so on. And again, what I just want to repeat myself, that I started working on this when I wrote my bachelor thesis. It was a lot of pain. I was like, oh God, I will never understand it. I think I still don't understand it fully, but I can work with it. And I would like to show you how to work with it. What is the logic behind it? Now, SPICE, as we saw here before, it's not provided in Python, but there are Python wrappers. And there's one Python wrapper, spiceypy. The link is also provided in the description, and it's automatically installed in our remote container session because it's in the requirements txt, and it's a wrapper for the C library. And yeah, spiceypy is also being provided in the description, so take a look at this. This is really cool work that has been done to get SPICE running in Python. Now let's go back to our script, or there's no script at all. Let's create a new script and we call it something like compute or comp Python earth I, pi, y, and b. So we have our Jupyter notebook, and let's see if we can import spiceypy. So yeah, it's loaded successfully, perfect. And what do we want to do? Now let's compute, for example, the position of and the velocity of planet Earth for today's date. Let's say midnight, for example. We can compute it for every second or even millisecond, but let's start simply with the midnight date. So we import date time, and we set a date. Let's call it date today, and then it's date time. Date time dot date. I forgot an e. Yeah, this happens. Daytime today. And SPICE requires certain formats for timestamps and even more. So let me just convert it to a string in a particular format. It's then str time, and then it's the year minus the month, and then minus the day. Then we have a t for time or whatsoever, and then midnight 00 00 00 00. There are also other formats. It's not the only one, but let's work with this one here. Let's load it. Yeah, it ran through, and now we can also print the date today. Make a quick copy out of it. So print the date, and it's today, the 30th September 2021. Now when I upload the video, it's on Sunday, so it's already October. So feel free to run the script then, or use even the command now to have a second precision, second resolution. Now, SPICE requires the time in certain formats, so it doesn't work with the UTC timestamp. It requires something that is called ephemeris time. Now, the ephemeris time is nothing but an float, and it gives you the time in seconds past a particular date. for example, the so-called J2000 date, so the 1st January 2000, 12 o'clock noon. This is just some astronomical definitions. So it was just introduced, and SPICE works with these ephemeris times. Now you may say, well, but why not use this timestamp? It's so simple and easy. Well, working with timestamps, it's hell. You have your local time, but there are also corrected timestamps considering relativistic effects. We have different time clocks, for example, for the satellites and here on Earth because of general relativity. Spacecraft have their own so-called spacecraft clock that has their own system. So time systems in astronomy and space science can be really, really confusing, and SPICE requires to convert everything in ephemeris time to keep these things working. Now we say, okay, good, let's use ET midnight, let's compute it, but, well, how shall we compute it now? And for this, okay, some functions pop up, but for this we have a documentation. Again, I know this is quite old-fashioned, but it's extremely detailed, so you can really get lost into it. You see also it's CSpice APIs. Again, spiceypy is a wrapper for the CSpice library. And here the most used CSpice APIs, for example, provides some descriptions for a lot of things, like, for example, converting the UTC to ephemeris time, or computing also the position and spacecraft of natural bodies, and so on. I will not click through all the documentation now for all the functions. I would like to show you hands-on the logic a little bit behind it, and the name of the functions. Well, I use there are some functions I have to look up, of course, and some that I use frequently, and yeah, I just write them down. And there will also be another thing that is very SPICE specific, but we will get to this point in a moment. So the command to convert is UTC to ET. Thankfully, this is a, well, self-explanatory command. And now I would say, yeah, we can print even the result afterwards to see how it looks like, and let's execute it. Oh, and there is an error. What happened? Now, the error comes from SPICE itself. It says no leap seconds, and there's some variable that points to some leap. So something is missing from a so-called kernel pool. So what is this? Well, SPICE itself is a very mighty library with a lot of also metrics operations and so on. But the position of the planets, the position, orientation of the spacecraft, they are not stored in the library, but they are stored in something called kernels. So the kernels are like configuration files or history data that contains this information that is, for example, computed by JPL, by NASA, or by the European Space Agency as well for their missions and their purposes. And these files need to be loaded. And you may ask, yeah, wait a second, why not put the data in the library? Well, the point is, if you want to have a library that is extremely huge, for example, covering all planet position from, I don't know, 10,000 BC to 100,000, to year 100,000, or, for example, also the trajectories of spacecraft, you get some preliminary results. There are also so-called kernels that predict a certain trajectory of a spacecraft, but later it may differ a little bit. So you don't want to cover all these cases in your library. You just want to have them as separate kernels where you have them stored, and it's that simple. So you just grab what you need. And, well, SPICE requires a lot of kernels. And now also your question maybe, yeah, but what kind of kernel do I need? And, well, that's the point. Either going into the documentation deeply, or, yeah, I just try to explain it. And today we will cover 2 or 3 kernels, but in the future we will use more and more and more kernels. And then you get, over time, you get a feeling what they mean. So for today, it will be overwhelming, of course, and also coordinate system and so on. Don't be bothered by it. Let's just write some lines of code and try it out. Now, where are the kernels stored? There are several repositories. One is from JPL, another one is also from ESA. The ESA one is also in the description. And let's see, what do we have here? Well, we have folders with different missions. For example, we have the Apollo mission. So hey, we can really compute the trajectory of the Apollo lander. So this is really nice. Cassini. I personally worked on the Cassini mission, so I know this folder. I know everything what's in there. It's I worked for years with it. And also other missions like Deep Impact we have here, Dawn. We have, for example, also the New Horizons, so we can also compute the flyby to Pluto and even reconstruct how the camera was pointing towards Pluto and what is the field of view and everything. So if you would like to really work with it, I mean, just write me. You know, I would like to show you the things that you are interested in. And if you say, hey, yeah, let's reconstruct New Horizons, come on, we can do it. It will take us like 5 or 6 videos or so, and then we are through and we have a better understanding of the mission. Pioneer Rosetta, the other mission I worked on the comet Churyumov of Gerasimenko. And then there's another folder called generic kernels. Let's go into this generic kernels folder. And each folder contains a txt file called aa-readme.txt, and this explains the content of the subfolders and so on. And we have different folders, DSK, FK, whatsoever. And they encode the kernel type. So LSK is the leap seconds kernel we need. And from all of these ones, we need the most recent one. It's called NIF 0012 TLS. So let's store this file. Let's download it in our project repository. Where am I? Here I am. The Earth. Not the Earth. I would like to do it here. And let's create a new folder, and I call it simply kernels. And now within kernels, let's create another one. We apply the same logic LSK, and here in LSK we can store it. Now the another kernel we need is also a kernel for computing the position of Earth. And these kernels are called SPK kernels. And here we have asteroids, comets, and so on, but we need the planet one. And let's take a look at this AA summary, because here are a lot of files. What are these files about? So let's take a look. What do we have? We have here a summary for a kernel called DE430 BSP. It contains the barycenter of Mercury, Saturn, Pluto, and so on, and also the Sun. Nice. We want to compute the distance from Sun to Earth. So we have also Earth here, which is good. And it covers a wide range of dates, so almost a millennium. We have also other kernels which cover even more, a larger date range, and one that is called 432S, which covers only 100 years. So this should be quite small. Let's take a look. We have 432S BSP, yeah, 10 megabytes. Let's download this one. Now you may say, wait a second, this is the time of big data. We don't care about megabytes or gigabytes or terabytes. I know, you're right, but I would like to provide all these kernels in my GitHub repository so that you don't have to click around in all these repos here, but by simply making a pull from my repository, you can directly start using it. So all the code I show will be also stored in the GitHub repository. So let's apply the same logic, SPK, and download it. Perfect. Now we can go back to our VS Code, and we can now, where is it? There, code. We can now load the kernels. So how does it do? How does it work? There's a function called furnish, and we just say, okay, let's go one directory back. I think we called it kernels lsk nif 0012 tls, and the second one is spiceypy furnish, and then kernels spk, and it was de432s.bsp. Yeah, it worked. Perfect. Now can we convert the time now? Ha, it works. Nice. So we have now our ephemeris time, and now we can compute the position of the Earth. Yeah, so also here, if you want to know how to compute everything, we can use again the documentation, computing positions of spacecraft and natural bodies. Yeah, so there are a lot of different functions. But yeah, let's use the one that I prepared for you and take a look what the logic is all about. So the function we will use returns two things. The one is a so-called state vector. So the state vector is a vector that contains the positional information, but also the velocity information. So it will have x, y, z coordinates and velocity x, velocity y, velocity z direction. The second output, so this will be a list, right? The second output is the so-called light time. And this is also pretty interesting. The light time is the time in seconds that the light needs from the observer to the target. So from Earth to Sun, it's, I don't know, I think something like 7 or 8 minutes. And the function we use is spiceypy, spk geo, and this requires 4 input parameters. The first one is the target. What object do we want to observe? We want to observe planet Earth. We want to observe Earth from the sun. I know technically the sun is not the center of the solar system, it's the barycenter of the solar system, but we will talk about the barycenter later. Not today, but in another video. And what do we write now? Is it now Earth or is it now Earth? I don't know. What is it? Well, Spice has its own logic, surprisingly. And this logic is called integer ID codes. So every spacecraft, every natural body has their own ID. And let's search for planet Earth. Ah, there it is. We have here a list with the NIF IDs. For example, the solar system barycenter is a 0, Mercury barycenter is 1, the Earth barycenter is a 3, and it's actually, yeah, the barycenter considering the moon, so it's not the center of the Earth. And for example, the 10 is Sun. So, okay, so yeah, the observer is the Sun, so you know the NIF ID for the Sun is 10. But yeah, I'm not 100% happy. I would like to have really the center of the Earth, and there it is. It's 399. So this is like the center of Earth. There are also other objects, as you can see. For example, Io, one of the moons, the larger moons of Jupiter. But this will cause an error probably if we compute the position to Io, because we did not load the kernels of Io. But we will get to this point also at some point. Now for us important is the ID 399 and the ID 10. Now let's get back to our VS Code. The target is 399. We have also the time, the ephemeris time, which is this one here. So today midnight. We also have, let's keep it clear. Again, I will also add comments and everything in the notebooks so that you can go through it with your own pace. So yeah, it will be a little bit more sophisticated, let's say. The reference frame. What is a reference frame? Now, I will get to this in detail in another session. For now, we will have a reference frame based on the ecliptic plane. So what is the ecliptic plane? I know the solar system, everything is 3D, but imagine you have a table, and in the center of the table is the sun, and the Earth is rotating around or revolving around the sun on this table. And this plane where the Earth is moving is called the ecliptic plane. And every other planet, the other planets have their own planes. And this tilt of the other planes is called inclination. So the angle between the plane of, for example, Jupiter and Earth. And since gravitational perturbances cause, some wobbling of the Earth, the ecliptic plane also wobbles a little bit, right, over time. And for this, we use the reference frame to the year 2000. Now, where do X, Y, and Z point? Well, I will talk about it in more detail when we get there, so otherwise it will be too much information, but for now this should be enough. And we have an observer, and the observer is the sun, so the number 10. We can also print the state vector and see, wait a second, this is wrong, where am I? Here. We can also print the state vector and see what the result is. Now, signs are also, it's always you need a quick estimation, right? It's also this kind of thing, you know, maybe from the interviews you hear about from some consulting company, how many smarties can fit into a smart or another car. It's like also, okay, what will the result make sense? Is this result something you expect? What do we expect? What do you expect? So, you know, out of the box, what kind of distance? And the distance should be something like 150 million kilometers. This is one astronomical unit. But the Earth is not circular around, revolving circular around the sun. It's more on an ecliptic plane. But it's always important when you do these calculations to have some idea in your thoughts. What do you expect? Because otherwise, yeah, you can get tricked, right? So always think about what do you expect, or create unit tests. And with the unit tests, you put your knowledge in there. So let's see. We have now 6 values. Okay, cool. Something huge numbers in kilometers and 3 smaller ones, kilometers per second. Well, let's compute the distance. Let's compute the distance from Earth to the Sun. Not use the print, but yeah, yes, let's use the Euclidean distance. We use the module math, and then Earth Sun distance is equal to math square root, and then we just apply the Euclidean distance. I know you can also use it with NumPy commands and so on, but yeah, here we will just do it in high detail. So now it's the x coordinate, the y coordinate. Now we have the z coordinate as well. And what do we expect? We expect something like 150 million kilometers, roundabout. So let's see, let's print it. And a huge number. We have 100 here, 100,000, million, 10 million, 149 million. Makes sense. Let's convert it to astronomical units. We can do this as well. Spice has its own built-in function, which is quite nice, so we can use it. Earth Sun distance in AU. It's spiceypy convert. And what do we want to convert? We want to convert the distance that is given in kilometers, and we want to convert it to AU. And then afterwards we print it as well. And there you see 1.0015 and so on astronomical units. So this makes sense probably. Now we can compute more parameters, and we will do it next time. For now, I think it's enough. I mean, it's for you a new library with new content, kernels and so on. I hope you will digest everything. I will also upload the code I showed you today. It's not a lot, but it's a lot to digest also with this kernels thingy and so on. And go maybe also a little bit through the documentation. Now, next time we will also verify our results, because I can show you anything, right? Here, some random numbers here, and it's 1 AU, okay, yeah, makes sense, but do these coordinates actually make sense? Does the velocity make sense? Is it something we can also expect from a theoretical point of view? This is always important in science, to question it, you know? I mean, not to obsessively question everything, right? But just to think, okay, does it make sense? Let's make a check. So next time we will make a small check, and then beside the Space Science with Python tutorials, I would also like to show you some commonly used toolkits and so on, web applications in space science for astronomy and so on, that can be used to verify these results, to get a better feeling and understanding, to see, does it make sense, or am I talking nonsense? But until then, I hope you enjoyed today's tutorial, and I'm glad you were here. Take care, guys, and see you next time.